Thank you, Hamid. Thank you, Damian, for a very good presentation. My name is Arash from University of Sussex in the UK, in the very south of UK in Brighton. My presentation today is about generally energy efficient control algorithms. And instead of focusing on the details of techniques, I would love to actually tell you a story, my story and my students' story during the past 10 years, that what we have done and what problems we try to solve, and maybe it can be useful for the audience. So if I want to give you the keywords of my research, I would say that energy efficiency is one of the major keywords, but I'm focusing on developing algorithms and control strategies considering this energy efficiency. And as a result, I would say that I'm working on efficient control algorithms. Applications, normally it's in a bit different applications, from renewable energy to vehicles, electrified vehicles, and also robots. So I would say that if I want to summarize my interest in research, I would say that novel energy efficient planning and control algorithms for different applications. So one of the keywords that thankfully Damian also mentioned, I just want to clarify it here, is energy management strategy. Actually, energy management strategy specifies a control problem of optimally managing energy flows with respect to, within a system with respect to one or more constraints to make sure that the energy demand is always met. But when we say energy efficient control strategies, normally we consider minimization of energy consumption, but as the secondary objective, means that we always want to meet the energy requirement, but meanwhile we want to minimize the energy consumption as well. Another keyword which is related here is the control allocation algorithm or problems, because most of the time these systems are called over-actuated systems, means that you can meet the energy consumption or energy requirement with different ways, and in most cases with infinite ways. Then the question is that which one is the best with respect to the secondary objective. And these kind of problems are normally called control allocation problems. So, as I said, it's a kind of case study by case study. I'm introducing you a few case studies which are related to the concepts that I mentioned. One case study is an energy management strategy for a standalone hybrid renewable energy systems. A standalone means that it's not connected to the grid. So these are small renewable energy sites, normally in remote areas, not connected to the grid. And also, when we say hybrid renewable energy systems, means that it has more than one type of renewable energy source, like wind turbine and solar panels together, or it could be different types. So not being connected to the network actually makes it a bit more complex and challenging from the control perspective, because the grid is can be assumed actually as an infinite capacity battery which is connected to your system, but without having it, actually all your capacities are, and particularly storage capacity is limited. Then the question is that how you can stabilize such a DC microgrid in a way that you can make sure that here, for example, this is a DC bus, the voltage of this DC bus is always within a range, and it means that you're managing the consumption and the production of energy, and also how you can share the power demand proportionally in a very, let's say, in a fair way between different sources of energy. And in another very important thing that we focused in this research was that when you have limited battery, the charging regime of that battery is very critical, because if you don't charge it properly, the batteries would be damaged very easily. And particularly when you don't have grid, here it means that you should be able to curtail or the production whenever it's required, in a way that you make sure that the batteries are charged properly. So we formulated such a problem as an optimal control problem, and then it has some challenges. Next slide I will show you. And then we develop a non-linear model predictive controller to solve it successfully. So the challenges of such a system is that, first of all, of course, it's non-linear system, but more than being non-linear is that at least two components of such a system are discontinuous, means that their operation changes completely with respect to some other events in the system. Means that, for example, battery is one of those discontinuous systems. The behavior of battery when it's charged is completely different from its behavior when it's discharged. Electric motor is another one, because its behavior when it's is doing the motoring is different from its behavior when it's doing generation. So these are main challenges of such a system, and then it lays two main issues to solve such a problem numerically. One is that, first of all, formulating such a problem is a bit difficult. And second is that formulating in a way that you can solve it with available tool sets is another problem. So actually, I don't want to go to the details. I just want to tell you the main approaches that we use that may be useful for the audience for their problem as well. First of all, we focus on a mathematical technique called complementarity constraints. And complementary constraints is very good to model the discontinuities. The good thing about complementarity constraints is that we have numerical tools to solve complementarity constraints. So in other words, we convert the problem of a discontinuous system to a problem with complementarity constraints that thankfully we can solve it numerically as well. So this is one way that we did. Complementarity constraints actually is shown in this equation. Actually, this is a symbol of it, but meaning is that at any time, either of the sides of the symbol would be in its boundaries. Means that at any point, either, for example, gamma 1 of gamma 1 is actually equals I battery stack, or gamma 1 is either 1 or 0. So every time that you get a sample, either of these conditions would happen. Then we used Modelica, and Modelica is a very good language, modeling language for modeling a system using directly the mathematical equations. And then there are tools that can compile Modelica language to equations, but we use an open Modelica, which is open source tool as well. So why is important? Because Modelica actually, with Modelica, you can validate and evaluate your developed model directly by using the developed equations. You can't do it easily in MATLAB, for example, or in Simulink, but in Modelica, you can do it, and it's designed for such a purpose. So as you can see here, we have given the equations of such a hybrid renewable energy system directly, and this is a model of that system. And then you can simulate and make sure that those equations work well and they are stable. And then you can use those equations for the development of your controller. Another technique or another tool that we use was to solve the optimal control, develop optimal control problem, that we use a tool called Casadi, which is developed in Belgium, where Damian is from, in the University of KU Leuven. And this is a very effective tool to formulate and solve the nonlinear MPC problems that we have used. But the point is that because the system is just discontinuous, that makes that solver a bit more complex in a way that you should make the sampling time variable over the time. So you can't have a fixed sampling time. So you should make the variable sampling time in order to find out the location of those discontinuities. So as a result, we solve it, and you can see that here the variation of the resources, wind and solar, and also torque demand, load demand, but still you can see that the voltage of the DC bus keeps constant within a range. And also by doing the curtailment, here you can see of the solar and the wind branch, the charging of the battery is with a constant current, with an increasingly current, slightly increased current, but at the constant voltage. And it helps to charge a battery for a larger SOC without damaging the battery. And it was the main purpose of this algorithm. Then we focus on another problem. The problem was on energy management strategy of electrified vehicles. In this case, it was a fully electric vehicles, but with multiple drivetrain. So it means that this car has 4 electric vehicles, 1 per each wheel. Then the question was that how we can manage or how we can use these multiple electric vehicles, electric motors, in a way that we can reduce the energy consumption, or in other words, with minimizing the energy consumption. Or in other words, that if having multiple electric motors can reduce the energy consumption of an electric vehicle or not. And we showed that yes, it can be. We formulated the problem. I'm not focusing on the detail, but again, this problem has the same issue that electric motors can be either working generator or motoring, and it should switch between them and cannot work at the same operation. And then the question is that when this should be switched off. The point is that we showed that such a problem can be solved for each side of the electric vehicles. So we simplified the problem. Then we also showed that, mathematically proved that the optimum solution cannot be a mix of each side, cannot be a mix of traction and generation. So the optimal solution of each side is either generation or traction, and this solved the problem. This made the problem very straightforward and simplified in a way that we converted the optimization problem to an algebraic problem. We showed that the optimal solution of each side is either single traction, means using just one of the motors, or even distribution, means using them equally. And then the question would be that when we should switch between them, that we formulated an algebraic equation that its solution tells us the torque of the switching. So by increasing the torque, there is a specific point, depending on the speed, that you should switch between even and single axle solution. So then we actually used this system that we had for deriving the power loss curves of the vehicle at each speed of the vehicle. We fit it to that power loss curves that the algebraic equation uses it, and then we solved it for each of the speeds of the car, and we found a switching torque for each speed. And as a result, the final solution was very simple, a simple lookup table that tells us that what should be the switching point of the torque of each side of the vehicle, depending on the speed of the vehicle. And putting it in the ECU of the vehicle, actually we showed that we can have up to 4%, up to 4.6% of energy reduction, depending on the driving cycle, test cycles of the vehicles. The third problem that we attacked was that if any look ahead information from the road can help us to improve or reduce the pollution of the engines. So it means that if I have a camera, as you can see here, that can see a part of the road ahead of the vehicle and use that information to improve the control of this engine, would it have any effect on the efficiency of the engine in terms of particularly pollution? Can we reduce the pollution of such an engine? And if yes, then how long of this look ahead information is effective? And finally, is that what is the technique we can use to exploit those look ahead information for controlling the engine? We answered all those questions. Actually, first of all, we did extensive statistical research, finding that about 2 seconds of look ahead information is enough, and particularly in the form of torque demand. So if we know torque demand of that our vehicle would experience within the next 2 seconds, it's effective, and we don't need to have more look ahead information. We did it, for example, by extensive autocorrelation and cross correlation analysis, some statistical terms, methods, and so on. And then we use the two-layer economic MPC technique. Economic model predictive control, unlike the general model predictive control, doesn't track the optimal solution, but by itself finds the equilibrium point as well. So it's called economic because it doesn't know what is the equilibrium point or optimal solution that it tracks. It finds it and tracks it both together. And then the result of it was controlling the turbocharger and the 2 EGR of a vehicle, that this vehicle was in production line on JLR. And we showed, based on our hardware in the loop simulation, that such a technique of look ahead information, exploiting look ahead information, can reduce the NOx by 9% and soot by 14%, as compared to the optimal controller without having that look ahead information. So this 9% and 14% is just the effect of look at, as considering the data in future. And it's good to know. It's good to note that the NOx and soot are contradictory. There is a trade-off between them, and improving NOx normally decreasing soot. Improving NOx degrading actually the soot emission. But we could find, by developing such an algorithm, we could find the optimal solution that the car manufacturer and the engine developers couldn't find it before, because generally the technique that they use in car manufacturing, in car industry, is that they do a lot of extensive tests and practical tests. However, not blind, but it has lots of theories behind, in order to find the solutions as lookup tables and put that lookup tables in the ECU of the car. But we showed that the extensive work that they had done was not able to find this optimal solution that our system could find it. And as a result, we could show that this is such a significant reduction in the NOx. And so this result has been patented as well in the UK. Then we came up with another problem. So as you can see, all about energy consumption and energy efficiency or pollution efficiency, but in different applications. Then we came across another question, research question, which is related to energy efficiency, but for connected and autonomous vehicles. That the question is that if having all the cars connected and autonomous vehicles, can we improve the throughput of intersections, and how it can be, or can we formulate such a problem and then solve it and show that the throughput of the intersection, having all the vehicles collaborative and autonomous, would improve the throughput. So we formulated again such a problem as the optimal control problem, and with some difficulties we solved it, and you can see the results here, for example, as a solution of such a algorithm, that how the vehicles would cross such an intersection if they are fully autonomous. For example, this is one case study. Next is a bit more complex case study. And yeah, so as you can see, the vehicles actually cross in a lane free and signal free, and we showed that using such a technique can improve the throughput of the intersection by about the percentage I can't remember. I can calculate now. Yeah, it's about 80%. And however, this is for a this is a benchmark that we showed that this value of the throughput is actually limited by the theories of the geometry. So this, and our technique could reach to that theory, that limit of the geometry, and we showed that we can use the results of such algorithm as a benchmark for any such algorithm that wants to control the signals of the intersection or controlling the vehicles. And finally, the last question that we came across was about in robotics. The question is interesting. It's within a class of problems called informative path planning. And the question is that if we can efficiently and in an energy efficient way control or plan the path of a robot with a single uncertain sensor to make a map of a completely unknown area. So in other words, is that we want to make a map of a completely unknown area. Then the question is that if without having anything about that map, we can find a close to the global optimal solution of such a problem. And we showed that our algorithm actually could find it as the solution, and then we find a benchmark for it. We compared and we showed that it works properly, making a map, ignoring the left-hand side. This is just the RRT star for obstacle avoidance, but these red points are the paths, and this bottom left is the most confident map that it generates. And then the question, this is the outcome of our algorithm. Then the next question was that, okay, can we benchmark it? So how we can compare the outcome of such algorithm, saying that this algorithm works properly or not properly. And then we defined a posterior problem, means that we assume that we know the map and we want to remap it. And finding the solution of such a posterior problem, which is a remapping of a known map, we assume it as a benchmark, and we showed that our algorithm follows the benchmark here, as you can see, which is a linear behavior of number of identified cells over the traveling time. So it shows that how linearly the number of identified cells increases. And our algorithm actually follows that trend of the posterior of the benchmark solution over a very good range of the time, up to about 60% of the time, before reaching to a kind of saturation, that it just moves a lot, but just for one cell or another cell. So I just want to finish my talk with one point, that when we want to test these algorithms that I mentioned, we reach to the point that we need a tool, and we develop a tool. We call it ROBIL, Robot in the Loop Simulator, that actually is a tool to test the collaborative or distributed algorithms. When you have multiple of robots, multiple of cars, and your algorithm should run on multiple of them, then it's a very expensive to test your algorithm in reality. Then the question is that if we can use the scaled down robots, for example, in case of cars, to do the middle test of such algorithms in a very cost-effective way. And we developed the ROBIL based on a technology called ROS, Robotic Operating System, and it's on top of it in a way that you develop your robot in a SolidWorks integrated into it, and then you use either this SolidWorks model as a digital twin of your real robot, or you use the real robot or a combination of them to test your algorithms. That this video shows the results, and this is a video of that algorithm for crossing the intersection that I explained before. That the bottom ones are the results of generated by MATLAB, and the top ones are the one generated by ROBIL, but one in the top left using the real robot, top right using the digital twin of it. So using this tool, we are testing the performance of our algorithms in a actually close to real situation for different algorithms that we have. Thank you very much for your time and your attention. Sorry, I think I was a couple of minutes later than expected.